Take a look at another example of the fundamental theorem of calculus part 2. This one's going to look a little different, but it's basically the same type of question. So we have big F of x, and again, this big F means the antiderivative of little f, okay? So big F of x is equal to the antiderivative of 1 over x squared from 0 to e to the x dx. So again, how do you know when you're dealing with fundamental theorem part 2? It's when one or both of the limits is a function itself. Now this lower limit is a constant number 0, but this upper limit is a function, e to the x. So this is our antiderivative function. It's equal to this. And what we want to ultimately do is evaluate big F prime of 3. Now you really know that you're dealing with fundamental theorem when you're taking the derivative of the antiderivative when the limits are functions. Okay, again, if the limits aren't functions and we take the derivative of this, we'll just get 0 back. But because this upper limit is a function itself, we know we're dealing with the fundamental theorem. And we're going a step further in this example. Once we take the derivative again of the antiderivative, we will then plug in 3. Okay, and we'll get an answer that deals with the rate in which the area under this curve is changing with respect to these limits. A little bit complicated and interesting, but the same steps as we did previously. So let's go ahead and do that together. Again, step 1 is to plug in the upper limit and multiply by its derivative. So ultimately what we're actually doing is we're taking the derivative of the original integral because it says big F prime. Again, the notation here is just different, but it means the same thing. So what does that mean? That means we're going to plug in the upper limit into our function 1 over x squared. So whenever there's an x, we're replacing it with e to the x, and then we're multiplying by the derivative of that. And remember, the derivative of e to the x is just e to the x. Okay? Now, I still like to follow the same rules, even though we know it's going to turn into 0, and that is for step 2 to subtract the lower limit when we plug it. Subtract the lower limit plugged into the function times its derivative. But the derivative of the lower limit is going to be 0 because it's a constant number. So even if this was a 7, 8, or 9, we'd still be multiplying by 0 because the derivative constant is 0. So I did plug it into the function, and then I multiplied by the derivative of 0, which is 0. And I just like to do these steps because it helps. I don't know, it's the same steps every time, and it helps me remember what to do. Just in case, let's say this lower function was a function, the lower limit was a function, and this upper limit was a constant, then the first part would be 0. The second part would end up being an actual function. So as long as you follow the steps, you're going to get the right answer every time. So again, notice this second part is going to turn to 0. All we have to do is focus on the first part. So the first part, I can take this e to the x, move it to the top, and then e to the x to the second power is just e to the 2x. Now, I've made this mistake before of writing this as e to the x squared. Remember, when you have an exponent to an exponent, you multiply the exponents. You don't raise it to an exponent again, and that's a very common mistake I've seen and I've done myself. So x times 2 is not x squared, it's 2x. Be very careful with that. Okay, so e to the x over e to the 2x, well, that's 1x and 2x. It's going to become e to the x on the bottom. And the final step is the original question, if we go back, said big F prime of 3. So once all that is said and done, we're just going to plug in 3 for x. This is our final function. So it's 1 over e cubed. That's the final answer. Okay, 1 over e cubed. Now you might be thinking, what does this answer mean? Well, I'm glad we did this example because when you plug in an actual number, it makes a little bit more sense. So first of all, let's just talk about the original integral. Well, let's actually talk about the function, right? 1 over x squared, right? We all know what that looks like. Basically looks something like this, if I'm not mistaken. Okay, it's always going to be positive. Now, the integral of this function, let's just choose numbers for now. -3 to 4 will just be the area under the curve of this in the x-axis. And of course, the x-axis is, whoops, use another color there. X-axis is down here. So let's say from -3 to 3, it'd be the area under the curve. Now, if we're going from 0 to the e to the x, That all depends on the x value, right? For example, if I made x equal to 1, this would be the area under the curve from 0 to e, right? So what you can see is that as the x value changes or it increases, the area under the curve is going to increase because you have more space right here. Okay, so what this question is asking is, first of all, we're taking the derivative. So the rate in which the area under this curve is increasing as x increases, right? And then we're plugging in 3. So what this question is ultimately asking is, at what is the rate of change of the area under this curve at from 0 to e cubed at x equals 3. So if we were to go from 0 to e cubed, which would be, I don't know, bigger than 10, less than 20, I guess, or maybe around 20. So from 0 to 20, at that particular point in time, what is the rate in which the area under this curve is changing? That's really what this question is asking. And the answer is 1 over e cubed. Okay, it's going to be a very small decimal. Let's go ahead and read this together. We learn a few things from this exercise. First, when an integrand's limit is a constant number, it has no effect on f prime of x, as the derivative of the limit equals 0. Second, it is important to find big F prime of x first before plugging in a number. And this is something that took me a while to wrap my head around. But the order in which you take the derivative is important. So in this first expression, we are taking the antiderivative first, okay, then taking the derivative and then plugging in the constant. That's the order. So antiderivative, take the derivative of that again, then plug in the constant. In the second expression, we're taking the antiderivative, plugging in the constant, and then deriving that. Well, that's going to give you 0 every time, right? So the order is very important. These two are not the same. Again, step 1 here is to find the antiderivative, same as here. But step 2 is to derive that. So you're taking the derivative function. Step 3 is to plug in the constant. Over here, step 2 changes. You plug in the constant first, and then you take the derivative. It doesn't work that way. It's always 0. Because the dx of big F of c always equals 0. Okay, that's it for this example. If you have any other questions about it or the rate in which the area under the curve of a graph is changing or any other questions about the fundamental theorem part 2, let me know.